Rogue planets sound like science fiction, cold, starless worlds drifting through interstellar darkness. But over the past decade, evidence has been mounting that they are not rare anomalies. They may be the dominant type of planet in the galaxy. The shift began in the early 2010 seconds when gravitational microlensing surveys like MOA and OGLE began detecting brief, sharp, brightening events in distant starlight. These events occurred when massive objects, often planet mass, passed in front of background stars, bending their light. The surprising part was the frequency. For every detectable microlensing event caused by a star, dozens appeared to be caused by objects with masses similar to Earth, Neptune, or Jupiter. The Milky Way, it seemed, might be filled with planets that have no parent star at all. By 2021, data from NASA's Roman Space Telescope simulations and new OGLE results suggested something extraordinary. There may be between 1 and 10 rogue planets for every star in the galaxy. Some estimates go even higher. A 2023 analysis in the Astronomical Journal modeled that the Milky Way could contain trillions of unbound worlds, ranging from frozen Earth-mass bodies to gas giant orbs larger than Jupiter. These planets drift in complete darkness, heated only by the slow decay of their radioactive cores or residual warmth trapped beneath thick atmospheres. Their origins are even stranger. Some were born free, forming in collapsing pockets of gas too small to ignite into stars. Others were evicted violently from their home systems, thrown out by gravitational interactions with giant planets, passing stars, or the chaotic reshuffling of early planetary formation. A few may have been stripped away during close stellar encounters or by the turbulent tides of galactic migration. In each case, the outcome is the same: a world cast into the void, carrying its geology and atmosphere into interstellar night. And yet, rogue planets are not cosmic debris. They are long-lived worlds. Unlike stars, they do not burn out. Unlike galaxies, they do not depend on cosmic structure for stability. Once adrift, they can persist for trillions of years, far longer than stars, far longer than galaxies, far longer than anything that shines. In the extreme far future of the universe, when the last stars fade and the cosmic background radiation cools toward absolute zero, rogue planets may be the final intact environments remaining. These starless worlds are not the exotic fringe of astrophysics. Increasingly, they look like the backbone of planetary reality. And if current models are right, the most common habitable environments in the universe may not orbit stars at all. They may drift in darkness. Rogue planets may seem exotic, but the process that creates them is not extraordinary at all. In fact, violent ejection is a natural byproduct of how solar systems form. When a young star is born inside a cloud of gas and dust, the material around it collapses into a spinning disk. Inside that disk, thousands of planetary embryos begin to take shape. Moon-sized bodies smashing together, merging, scattering, and reorganizing in a gravitational free-for-all. For millions of years, this process is chaotic. Orbits overlap, bodies collide, and many of them lose the celestial lottery. Computer simulations of early planetary formation, including the landmark 2000 and 22,023 Newton's body models run by the University of Zurich and JPL, show a consistent pattern. Young solar systems tend to overproduce planets. There are simply more forming bodies than stable long-term orbits. This means the early solar system behaves less like a clock and more like a pinball machine. When two giant embryos pass too close, one gains energy and flies outward. If it gains enough, the star's gravity can no longer hold it, and it escapes into interstellar space. In some simulations, up to half of all forming planets are ejected before the system calms down. The presence of massive gas giants increases the violence dramatically. A single Jupiter-mass planet can destabilize entire regions of a disk, pulling smaller worlds into elongated orbits, slingshotting them outward. or sending them into the star. The same mechanism likely operated in our own solar system. Models of early Jupiter and Saturn migrations, particularly the Grand-Tack hypothesis, suggest that several early Earth mass worlds may have been thrown into deep space long before Earth itself stabilized. Those lost siblings, if they existed, are still out there today, cold, unlit, and drifting. Stellar neighborhoods can be equally unforgiving. Most stars are not born alone, they form in dense clusters where close encounters are common. If another star passes within a few hundred astronomical units, its gravity can distort planetary orbits, tugging worlds out of their systems like loose threads. The Gaia spacecraft has already identified dozens of past stellar flybys in our region of the galaxy. Some close enough that had planets been in fragile orbits, they could have been stripped away. Even mature solar systems are not safe. Over billions of years, gravitational resonances, wandering stars, and galactic tides continue to sculpt orbits. Any planet placed slightly too close to a giant neighbor can slowly drift outward until one close encounter ejects it entirely. That means rogue planets are not only born in chaos, they can also be created by slow, steady drift over cosmic time. The important revelation is that ejection is not rare. It is the default outcome of messy, gravitationally crowded environments. Planets are made by the billions, but stable orbits are precious. Every solar system creates losers' worlds that form normally, develop atmospheres, perhaps even oceans, and then are thrown into the dark. Each rogue planet is evidence that solar systems are not serene, orderly structures. They are sculpted by violence. And in that violence, some planets lose their stars, but not necessarily their potential to host life. For most of scientific history, the idea of a planet drifting through interstellar space sounded like a death sentence. Without sunlight, a world would freeze solid, its atmosphere collapsing into ice, its oceans turning into rock. A rogue planet seemed like the most sterile environment imaginable. But modern astrophysics tells a different story. A far stranger, far more hopeful one. A planet without a star is not automatically a dead planet. In some cases, it may be more habitable than worlds orbiting suns. The key is internal heat. Every terrestrial planet begins life with vast thermal energy trapped inside it, leftover heat from formation, radioactive decay, and tidal friction. Earth, for example, still holds enough geothermal power to keep its mantle partially molten after 4.5 billion years. Even if the sun vanished tomorrow, Earth would not instantly freeze. Heat from within would continue to push upward. On a rogue planet, that internal heat becomes the primary driver of climate. This possibility was first taken seriously after the discovery of Steppenwolf planets, a term coined in a 2011 paper published in Astrophysical Journal Letters. The authors argued that a rogue Earth-sized planet could maintain a liquid subsurface ocean kept warm by geothermal heat beneath a surface ice layer hundreds of meters thick. Think of Europa or Enceladus, but scaled up to the size of Earth. In other words, a planet wandering through interstellar space could still host oceans, chemistry, and potentially life. But the story becomes even more extraordinary if the planet retains a thick hydrogen atmosphere. Hydrogen is an exceptional insulator. It traps heat with remarkable efficiency, far better than nitrogen or carbon dioxide. A 2014 study from the Harvard-Smithsonian Center for Astrophysics demonstrated that a rogue planet with a dense hydrogen envelope could maintain surface temperatures above freezing indefinitely, even in total darkness. With enough insulation, geothermal energy can create a warm, ocean-bearing surface environment, not just an underground refuge. This means a rogue planet could have Earth-like conditions while drifting between the stars. Evidence is mounting that such conditions are not theoretical. JWST observations of free-floating substellar bodies, objects too small to be stars but too warm to be cold, suggest that thick, insulating atmospheres are common in young planetary systems. If even a small fraction of ejected worlds hold onto hydrogen shells, then countless warm, starless oceans may be roaming the Milky Way right now. There is another twist. No star means no stellar radiation, no ultraviolet sterilization, no solar flares, no harmful space weather. Life, if it emerged in deep oceans or geothermal vents, might evolve in complete stability for billions of years. A rogue biosphere could outlive every star in the galaxy. Rogue planets begin as exiles, but they do not necessarily end as frozen tombs. Many become hidden ocean worlds, thermally alive, chemically rich, and protected from cosmic hazards by isolation itself. These are not failed planets, they are survivors. If a rogue planet can keep liquid water beneath its frozen surface, or even maintain a warm surface ocean under a thick hydrogen atmosphere, then the next question becomes unavoidable. Could anything actually live there? The surprising answer from modern astrobiology is yes. Not only could life survive on a starless world, it might thrive. The foundation of this possibility comes from a discovery made here on Earth. At the bottom of our oceans, far from any sunlight, entire ecosystems flourish around hydrothermal vents, towering mineral chimneys, powered not by the sun, but by geothermal energy. These vents spew hot, mineral-rich fluid into the icy deep, feeding microbial communities that use chemosynthesis instead of photosynthesis. They extract energy directly from chemical gradients, creating biological networks completely independent of starlight. This was a turning point in planetary science. It proved that sunlight is not a prerequisite for life, only energy and chemistry are. And rogue planets have both. A starless world with internal heat could host thousands of hydrothermal vent fields across its ocean floor. Microbial life could arise in these vents, adapting to dark oceans warmed from below. Over billions of years, far longer than Earth's stable surface environment has existed, these ecosystems could diversify, filling the entire global ocean. The biomass might even exceed that of sunlight-dependent worlds, because geothermal energy on rogue planets is steady, not tied to day-night cycles or solar variability. But life on a rogue world wouldn't just be microscopic. It could become complex. On Earth, vent ecosystems support tube worms, clams, crustaceans, and even fish-like predators. If a rogue planet has Earth-like gravity, mineral-rich water, and sustained geothermal flow, there is no known biological barrier preventing more complex organisms from evolving. They would never develop eyes in the traditional sense, but they might evolve pressure-sensitive organs, thermal sensors, electroreception, or even sonar-like communication adaptations suited for pitch-black oceans. And these oceans could be enormous. On a hydrogen-insulated rogue planet, the sea may extend for kilometers above the mantle, creating more habitable volume than all the liquid water in the solar system combined. Life would not be a local oddity. It could blanket an entire planetary ocean. The most extraordinary part: these ecosystems could be far older than Earth's biosphere. Rogue planets are effectively immortal. They do not rely on a parent star's stability. They are not threatened by solar evolution, stellar flares, or planetary orbital drift. While Earth will become uninhabitable in roughly 1 billion years as the sun brightens, a rogue planet may remain life-bearing for tens of billions of years, long after every star in the Milky Way has faded. In the deep future, when the galaxy turns dark, the last biospheres might not be orbiting stars at all. They may be drifting through interstellar night, silent, warm, and alive. Rogue planets are not just planets without stars, they are survivors. Unlike worlds tied to stellar life cycles, a rogue planet's environment is dictated by internal physics, not the fate of a parent, Sunday. And that means when stars die, fade, or explode, rogue planets simply keep going. They are the cosmic equivalent of deep-sea creatures untouched by storms on the surface. To understand why these worlds endure, we have to examine the forces acting on a planet once it's freed from its star. When a planet drifts into interstellar space, whether ejected during chaotic gravitational interactions or kicked loose by a dying star, it loses solar heating instantly. But the dramatic temperature drop doesn't kill it. Instead, the planet becomes governed entirely by internal heat, generated by radioactive decay, residual formation heat, and tidal stresses, if it once had moons or a captured companion. This geothermal energy declines extremely slowly. On Earth, radioactive decay will continue warming our interior for tens of billions of years, long after the sun has died. A rogue planet, insulated by thick rock, ice, or hydrogen, retains this heat even more effectively. That's why models show its subsurface ocean barely changing temperature, even over cosmic timescales. But what truly makes rogue planets long-lived is that they escape the constraints of stellar evolution. Every star follows a predictable arc: hydrogen burning, expansion into a red giant, collapse into a white dwarf, or detonation as a supernova. Planets in orbit are at the mercy of this timetable. Earth, for example, will be sterilized roughly 1 billion years before the Sun becomes a red giant, simply from the gradual increase in solar luminosity. Rogue planets experience none of this. Once they are free, they enter a regime defined by physics that moves at a much slower pace. Their atmospheres tell another part of the story. A rogue world wrapped in a dense hydrogen envelope can trap heat so effectively that its surface temperature might remain above freezing indefinitely. Hydrogen acts like a thermal blanket, thousands of times more insulating than carbon dioxide. Even as internal energy leaks outward, the atmosphere prevents catastrophic cooling, and unlike atmospheres around sunlit planets, hydrogen isn't stripped away by stellar winds or ultraviolet radiation. It remains stable for geological ages. This stability gives rogue planets a unique cosmic advantage. They can continue evolving while orbit-bound planets are destroyed or sterilized. Even civilizations, if they formed there, could theoretically persist long after star-dependent species have disappeared. The harsh truth is that stellar systems are temporary. They live for billions of years, but not forever. Suns burn out, galaxies dim, energy sources fade. But rogue planets, drifting alone through cold interstellar space, experience no such countdown. Their energy budgets shrink slowly and predictably, giving them lifespans that exceed the age of the universe. And when the last stars die, white dwarfs cooling into black dwarfs, red dwarfs flickering out, after trillions of years, the galaxy will go dark. But rogue planets? They will still be there. Ancient, wandering, unchanged, and possibly still carrying oceans beneath their frozen exteriors. In the universe's far future night, these worlds may be the final homes of complexity, chemistry, and even life itself. If rogue planets are the worlds that outlive stars, then the next question is unavoidable. Could they also become the last homes of intelligent life? For a civilization bound to a star, the long-term outlook is grim. Every sun grows hotter with age, destabilizing climates long before it dies. Habitable zones drift outward, oceans boil, atmospheres escape. Even if a species masters planetary engineering, there is a hard limit. You can't negotiate with stellar evolution forever. Eventually, the star wins. Unless you leave. Rogue planets offer something most cosmic real estate doesn't: independence from stellar death. A civilization that migrates to, or originates on, such a world is no longer tied to the life cycle of any one star. Its environment is driven almost entirely by internal heat, radioactivity, and insulation, all of which change on timescales far longer than stellar lifetimes. To imagine how future civilizations might use them, start with the basics. A large rogue planet with an Earth-like or super-Earth mass, a thick hydrogen atmosphere, and a deep subsurface ocean could host temperatures compatible with liquid water at depth, even while its surface sits at hundreds of degrees below zero. For an advanced species, that is not a problem, it's a design brief. Cities could be built in pressurized caverns beneath the ice, close enough to tap geothermal heat, shielded from cosmic rays by kilometers of rock and water, energy would look very different from the way we think about it now. There would be no solar panels, no day-night cycle, no seasons. Power might come from deep geothermal wells, nuclear fusion, or advanced technologies we can only sketch today: black hole energy extraction, carefully controlled matter-antimatter reactions, or ultra-efficient recycling of waste heat. The key is that on a rogue planet, every watt counts, but every watt is also stable over immense spans of time. There is also a strategic advantage. In a universe where galaxies thin out and stars go dark, the most dangerous forces, supernovae, gamma-ray bursts, active black holes become rarer, but they never disappear entirely. A planet floating in interstellar space, far from dense star-forming regions, is naturally shielded from most catastrophic events. No supernova next door, no red giant phase to engulf it, no stellar flares to strip away its atmosphere. As a long-term bunker against cosmic disaster, a rogue planet is almost ideal. For a highly advanced civilization, rogue planets might not just be refuges, they might become vehicles. Give a drifting world guidance. Reaction drives anchored into its crust, gravitational tugs from captured asteroids, or even gigantic magnetic sails interacting with the galaxy's weak interstellar medium. Over millions of years, a civilization could steer its planet like a slow, armored arc, choosing safer regions of the galaxy or following resources as structures evolve. It is also possible that the first civilizations to reach extreme longevity are the ones that make this move early. As stars age and planetary systems destabilize, societies that remain tied to their original suns will face escalating engineering challenges. Those that transition to rogue habitats, deep, insulated biospheres built on drifting planets or planet-sized constructs, decouple themselves from that countdown. In the far future, the only civilizations still active may be the ones who embraced darkness. From our perspective, life on a rogue planet sounds claustrophobic. No open skies, no sunrise, no constellations. But for a species born into such a world, that may simply be normal. Their myths would not be about dawn and dusk, but about the ancient heat in the rocks beneath them, and the faint neutrino whisper of dead stars far away. In the very long run, as galaxies dim and the universe cools, the question of survival won't be about thriving near stars. It will be about mastering thermal economics in a cold, thinning cosmos. Rogue planets offer the one thing that matters most in that era: time. They don't promise comfort. They don't guarantee safety. But they offer a stable platform, dense, shielded, and long-lived, on which the last chapters of intelligent life could be written. If there are civilizations out there already thinking on trillion-year timescales, they may not be building megastructures around stars. They may be quietly moving into the dark. Rogue planets are not truly still. Even without a star to anchor them, they move relentlessly, silently across the galaxy. And understanding that motion is the key to understanding their role in the deep future of the universe. A rogue planet is not a drifting accident. It is a traveler, following a trajectory written by gravity, chance, and cosmic history. Most rogue planets begin their journey violently. Young planetary systems are chaotic places where gravitational shoves between giant planets can eject smaller worlds entirely. Others are thrown out when stars die, collapsing into white dwarfs or neutron stars and shattering the delicate orbital balance of their systems. A few are the remnants of galactic collisions or close stellar passes that rip planets from their orbits like fruit from a branch. However they begin, once free, they fall under the galaxy's gravitational field, becoming long-term wanderers in an enormous, curved arena. Inside the Milky Way, these worlds follow paths similar to stars, completing one orbit around the galactic center every 200 to 250 million years. But unlike stars, they aren't luminous beacons. They are invisible stones in a dark river. They drift in the galactic disk, occasionally rising above or dipping below it, influenced by the tides of spiral arms and the pull of passing star clusters. Over billions of years, a rogue planet might visit regions of high star density, then slide into almost empty stretches of interstellar medium, where the nearest star is light years away. Because they emit almost no light, we only detect them through rare gravitational microlensing events, brief brightening of background stars as a rogue planet passes in front of them. Those detections tell a surprising story. Rogue planets are common, perhaps even more common than stars. Some estimates suggest there may be trillions of them, with tens of billions in the Milky Way alone. Many are Jupiter-sized or larger, but a significant fraction appear to be Earth-mass worlds, planets, roughly like ours, except utterly alone. What makes rogue planets fascinating is how dynamic their journeys really are. Although they drift on stable galactic orbits, their paths are constantly perturbed by encounters with stars, giant molecular clouds, and dark matter concentrations. Each close pass subtly alters their momentum. Over cosmic time, these nudges accumulate, sending a rogue planet into new regions of the galaxy, sometimes sweeping it through dense stellar neighborhoods where the odds of passing close to habitable systems increases dramatically. This has profound implications for panspermia, the idea that life could spread between star systems. Rogue planets, shielded by thick oceans or deep crusts, could serve as biological carriers, preserving microbial life for billions of years. If such a world drifted through a young planetary system, fragments knocked loose by impact, events could carry spores or organic material to the newborn worlds within it. In this sense, rogue planets could be the interstellar bridge connecting otherwise isolated pockets of life. But for advanced civilizations, the motion of rogue planets offers something even more strategic. Because their trajectories are influenced by gravitational tides, they can be predicted and exploited. A civilization capable of deep space engineering could alter a rogue planet's path using mass drivers, controlled asteroid impacts, or vast magnetic sails interacting with the galaxy's plasma environment. Over hundreds of thousands of years, those forces could shift the planet's course by significant distances, allowing a society to guide its drifting home toward useful regions of the galaxy. In the far future, when stars wane and galaxies grow cold, these moving planets may form the backbone of a different kind of cosmic civilization. Instead of solar-powered empires, there could be slow-moving networks of rogue world societies, each traveling on its own arc, occasionally passing near others and exchanging information before drifting apart again. Communication would be rare, alliances long-lived, and time measured not in years but in millions of orbits around the galactic core. A rogue planet's journey is slow, but it is not aimless. It is a dark odyssey, carrying whatever it holds, oceans, microbes, civilizations, through the vast architecture of the Milky Way. And in a universe where everything else depends on the fragile fire of stars, these silent travelers may be the only worlds built to last the entire age of the cosmos. When every star has faded and the galaxies grow dim, the planets without suns may be the ones still moving. For a long time, astronomers assumed that a planet without a star was a dead world, frozen, airless, and lifeless. But that assumption collapses the moment we look deeper into the physics of planetary interiors. A rogue planet may lack sunlight, but it does not lack energy. In fact, many of these worlds carry internal power sources that could keep them warm, active, and potentially habitable for billions of years, long after their parent stars have died. The first and most important source is residual heat. When planets form, they accumulate enormous gravitational energy as gas, rock, and metal collide and compress. Earth still radiates much of this heat today, 4.5 billion years after its birth. A rogue planet, especially a massive one, can retain that primordial warmth deep below its crust. This internal furnace can drive convection, volcanism, and even subsurface oceans insulated by thick layers of rock and ice. A rogue super-Earth or mini-Neptune could stay geologically active for far longer than a sunlit world of the same size. But the real miracle is radioactive heating. Elements such as uranium, thorium, and potassium decay naturally inside planetary mantles, releasing steady heat for billions of years. This heat doesn't care whether the planet orbits a star, it just flows persistently, like embers glowing in a cosmic night. On Earth, radioactive decay provides a significant fraction of the energy that powers plate tectonics. On a large rogue planet, it could maintain a warm interior and a global ocean sealed beneath a shell of ice hundreds of kilometers thick. Then there is the phenomenon that gives rogue planets their electromagnetic hearts, planetary dynamos. If a rogue planet has a molten metallic core like Earth's iron-nickel engine, and if it rotates fast enough, it will generate a magnetic field. That field can be immense. Without a star's wind to confine it, a rogue planet's magnetosphere could expand to colossal dimensions, forming a protective bubble that stretches millions of kilometers into space. Inside that bubble, radiation levels would be low. Charged particles would be trapped in belts, just like Earth's Van Allen belts, but with far more stability over deep time. A powerful magnetic field has a second, subtler role. It helps retain an atmosphere. Even in the cold vacuum between stars, a rogue planet with a strong magnetosphere could hold onto a thick atmosphere of hydrogen, nitrogen, methane, or ammonia. Hydrogen atmospheres in particular are extraordinary insulators. A planet wrapped in a deep hydrogen blanket could keep its oceans liquid, even with no starlight, simply through the greenhouse effect of compressed gas. This may be the hidden key to understanding rogue habitability. A thick atmosphere acts like a thermos, trapping the internal heat and preventing the surface from plunging to absolute zero. Some models even predict Earth-like temperatures on the surface of a hydrogen-rich rogue planet, maintained entirely through geothermal and radiogenic energy. Such worlds could be warm, storm-filled, and potentially biologically rich, floating through the galaxy in total darkness. There's another potential source of energy: tidal heating. If a rogue planet carries moons, and many should, since moons are formed during planetary birth, not by stars, gravitational tug-of-war between planet and satellites could generate tremendous internal heat. Jupiter's moon, Io, the most volcanic object in our solar system, is powered almost entirely by tidal friction. A rogue gas giant with several large moons could have a miniature solar system-like structure of heated, active worlds orbiting it. For advanced civilizations, these energy sources are not limitations, they are opportunities. A rogue planet's internal heat is constant, predictable, and long-lasting. Deep geothermal wells could power megacities. Magnetic fields could be harnessed for induction energy, particle collection, or propulsion systems. Even the slow decay of radioactive isotopes could be engineered into long-term reactors embedded in the crust. This changes the very definition of what a habitable world is. Life does not need a Sunday. Light is optional. Temperature can be manufactured. Oceans can exist in total night. Energy can come from rock, decay, motion, and magnetism. A rogue planet might be dark on the outside, but inside, beneath ice, beneath stone, beneath crushing layers of atmosphere, it could be alive with motion, heat, and possibility. In a galaxy filled with dying stars and expanding voids, these electromagnetic hearts may represent the most stable, longest-lived environments for life. If the stars fade, these worlds keep glowing. Long after the Milky Way collides with Andromeda, long after every sun-like star burns through its hydrogen and collapses into a white dwarf, long after the galaxy loses its shape and drifts toward cosmic darkness, rogue planets will still be here. These wandering worlds are not passengers of the universe, they are its survivors. And in a future where galaxies dim and gravity loosens its grip, rogue planets may become the longest-lived objects capable of supporting energy, structure, and potentially life. The key is simple. Stars die quickly. Planets do not. A sun-like star lives around 10 billion years. A red dwarf may stretch to 1 trillion, but a rogue planet, freed from any stellar consumption or tidal stripping, can persist for timescales that make even red dwarfs seem temporary. Planets are small, cold, and incredibly stable. They do not fuse, they do not collapse, and they do not burn. Their internal heat decays slowly, their magnetic fields fade even more slowly, and their cores can stay warm for trillions upon trillions of years, far longer than the universe has existed so far. In the far future, when galaxies dissolve and star formation slows to zero, most energy sources will vanish. Starlight will fade, supernovae will stop, even black holes will begin to evaporate through Hawking radiation. But rogue planets remain structurally intact. They drift between remnant stars, brown dwarfs, neutron stars, and black hole husks, untouched, unbroken, and insulated from catastrophic gravitational interactions. Their sheer number ensures their survival. The galaxy may hold hundreds of billions of them, perhaps more than it holds stars. And while stars die violently, planets die quietly if they die at all. A planet can only be destroyed by collision, tidal disruption, or engulfment, but a rogue planet avoids all three by leaving its star behind. It slips into a form of cosmic retirement, coasting through interstellar space with no external forces to tear it apart. The universe tends towards simplicity over time, and rogue planets are already simple, low-energy objects. They are built to last. The deeper we look into cosmic timelines, the more astonishing their longevity becomes. In 10 to the power of 14 to 10 to the power of 16 years, star formation ends. But rogue planets remain. In 10 to the power of 17 to 10 to the power of 20 years, galaxies evaporate as their stars drift apart. Rogue planets simply drift with them. In 10 to the power of 21 to 10 to the power of 25 years, white dwarfs cool into black dwarfs, neutron stars fade, and even stable orbits disintegrate under gravitational decay. Still, rogue planets persist, especially the massive ones, whose cores can retain warmth for nearly unimaginable durations. Eventually, the universe enters the so-called degenerate era, a time with no starlight, no fusion, and almost no free energy. But even then, rogue planets remain geologically active in their interiors. Radioactive decay will still occur. Crustal pressures will still shift. Subsurface oceans insulated by kilometers of ice and hydrogen could remain liquid for quadrillions of years. And if life ever arose in those oceans, it would experience time differently, with no day, no night, no seasons, and no stellar cycles to endanger it. Rogue life could evolve slowly, steadily, and safely in environments that scarcely change. There is also a more speculative possibility. As the universe stretches and cools, large-scale structures may decay into stable planetary mass remnants. Objects the size of Earth or Neptune could become the default survivors of cosmic entropy, the last islands of complexity in an ocean of cold darkness. If so, rogue planets will not merely outlive stars, they will outlive meaningfully structured matter. From a cosmic perspective, rogue planets may represent the universe's final habitats. They require no sunlight, no orbit, and no stellar protection. Their lifespans exceed those of galaxies, clusters, and black holes. They are the slow-beating geological hearts of a dying cosmos, capable of storing liquid water, magnetic shielding, geothermal activity, and energy gradients long after the rest of the universe has gone still. When the last star flickers out, when the last galaxy dissolves, when time stretches into the farthest eras of existence, the universe will not be lit by suns. It will be shaped by worlds that never needed them. In the deep future, after galaxies dissolve, black holes evaporate, and the universe cools toward absolute darkness, rogue planets may become more than survivors. They may become vessels, carriers of chemistry, memory, and perhaps even intelligence across eras of cosmic time that no starbound civilization could ever endure. When every other structure has collapsed or cooled beyond use, these drifting worlds may represent the final places where complexity can still exist. What makes a rogue planet uniquely suited for this role is that it is both protected and isolated, shielded by thick atmospheres, deep oceans, and layers of rock and ice. Its internal environment is decoupled from the hostile universe outside. Even as the cosmos cools to a near-frozen vacuum, a rogue planet's interior remains warm through the slow burn of radioactive decay, tidal stress from metallic cores, and the residual heat of formation. Earth's core, for example, will stay molten for tens of billions of years, even without the Sunday. Scale that longevity up to ice giants, super-Earths, or hydrogen-rich worlds, and you have objects that remain habitable inside for quadrillions of years. Now imagine these planets drifting endlessly through intergalactic darkness, each carrying its own biosphere, microbial, aquatic, subterranean, or even technological. A starbound civilization is limited by the life cycle of its sun, but a civilization that migrates into a rogue planet's interior could remain active long after stars fade. With fusion reactors, geothermal extraction, and even vacuum energy harvesting, it could generate power without sunlight. Without a day-night cycle, biological rhythms could be re-engineered. Without cosmic radiation, evolution could proceed at its own pace. Rogue planets offer stability in an unstable universe. The implications extend far beyond survival. Rogue planets can move freely. They are not locked into orbits, not tethered to stellar systems, not shaped by radiation bursts or gravitational disruptions. They drift through interstellar and intergalactic space, carrying whatever life or intelligence resides within them. In a distant epoch, when galaxies themselves evaporate, these worlds become the universe's last travelers wandering through emptiness, preserving fragments of complexity long after the cosmic stage has gone dark. This leads to a provocative possibility. Rogue planets may be the universe's natural seeds. In the same way, meteors deliver organic molecules between planets, rogue planets may deliver entire ecosystems between galaxies. During close passes by young systems, they could shed atmospheric gases, ice fragments, or microbial ejecta. They could seed chemistry or even life into new worlds. Over cosmic cycles, rogue planets might act as the carriers of biological potential, slow, ancient, wandering arcs drifting across the universe. But the most profound possibility concerns intelligence. As the universe enters its degenerate era, civilizations may eventually realize that long-term survival requires abandoning stars altogether. Energy harvesting megastructures fade, stellar engineering becomes impossible, the cosmic background cools. But inside a rogue planet, insulated and stable, a civilization could potentially extend its existence beyond the era of starlight. Over trillions or quadrillions of years, such civilizations might miniaturize themselves, digitize consciousness, or integrate with their geology. They may not build starships, they may become the world they live inside. In this view, rogue planets are not only survivors, they are transitions. The final step in cosmic evolution before complexity becomes internalized, before the universe becomes too cold, too thin, and too dark for anything except the most insulated structures to endure. And far into the black hole era, the degenerate era, and even into the dark era of the universe, when the last particles decay and space-time stretches into near-nothingness, these planets may still drift dark, silent, preserved. It is possible that the last life, the last intelligence, the last memory of the universe will not live on a starlit world at all, but deep beneath the frozen crust of a rogue planet warmed only by the faint, ancient heartbeat of radioactive decay. In the final ages of time, the universe does not belong to stars. It belongs to the worlds that learn to survive without them.